Welcome back to Math 160. We are going to finish our last set of notes, that is chapter 9 on hypothesis testing. So let's take a look. Here we are. We're going to flip this page and let's get started. So I'm going to read the very top and then I'll ask for a volunteer to read parts A, B, and C. So we noted earlier that one of the statistician's most important jobs is to draw inferences about the population based on samples taken from the population. Decisions concerning the value of a parameter are obtained by hypothesis testing. Remember that a parameter is essentially a numerical descriptor of the population. So volunteer, please, to read the definitions A, B, and C. Come on, don't be shy.
I'll read.
Yay, thank you.
Okay. Hypothesis, a statement or a claim that something is true. Statistical hypothesis test, a process by which a decision is made between two opposing hypotheses. It is a procedure for testing a claim about a property of a population. C, there are two hypotheses involved in making a decision. One, null hypothesis, which is h to the 0, the hypothesis that will be tested. Generally, this is a statement that a population parameter has a specific value. This will be our starting point for the investigation. Usually, the null hypothesis represents a statement of no difference, no change, or no effect. One note, the equals symbol will always go with the null hypothesis. Two, note, if you see the phrases almost or at least or no more than or it is in your claim, this will be your null hypothesis. Two, alternative hypothesis, H to a statement about the same population parameter that is used, the null hypothesis. Generally, this is a statement that specifies that population parameter has a value that is somehow different from the value given in the null hypothesis. The rejection of the null hypothesis will imply the likely truth of this alternate hypothesis.
Aha, so thank you so much, Donna. So we have two hypotheses. We have the null hypothesis, which is the boring hypothesis. This is the one that says, hey, business as usual. There are no special changes. It's exactly what we thought it was going to be. This is no big deal. That's what the null hypothesis is, essentially. It's the one that's boring. No big deal. There are no changes. Nothing special is going on. Your alternative hypothesis is essentially what we are looking at in terms of something being different, right? We're trying to see, is there something special going on? Are we just accepting the null hypothesis, or does this particular sample, does this particular information, this evidence show that there's something different going on? So we're trying to decide on whether or not we're actually going to reject the null hypothesis, like say, no way, there's definitely something special going on, or we're going to fail to reject the null hypothesis, which means you don't have enough evidence to say that the null hypothesis is not true. That's what we're doing in this unit. You're either rejecting the null or you're failing to reject the null. Does that make sense to everyone? That does not mean you're saying, hey, the alternative hypothesis is the way to go. You're essentially saying, is it business as usual or not? Right? Is it business as usual or not? I want you to think of it that way. Let's look at part D. You just read in an article that the average person watches 12 hours of television per week. You believe that today, the amount of time people watch television is different than 12 hours per week. Notice the language that was used. Different than 12 hours per week. What this implies is that you believe that it's either less than or greater than, but it's not equal to. So what that means is you're essentially saying it is not equal to 12. The average watch time is not equal to 12. So I set up the two hypotheses for you, but I wrote it out in words just so that you can understand what we're saying here. The null hypothesis, the business as usual hypothesis, is that the population mean is equal to 12 hours. That's business as usual. But as a researcher, you're like, I don't agree with that. I think it's different, right? And if it's different, you're saying that the mean watch time is not equal to 12. That could mean two things. It could be less than 12 or it can be greater than 12. That idea right there tells us that this is going to be a two-tailed test. Do you remember that normal curve? And you remember how we talked about the middle, like 80%, 90%, 98%, and then we talked about the probability or the areas in both tails? When you have a two-tailed test, it literally looks exactly like this. From your last unit, would you please take out your T table? You may have to go grab that. So let me just pause the recording for a moment. Okay, so after writing out our two hypotheses, right, the null and the alternative, there are two decisions we can make. If you reject the null hypothesis, you have shown that the average could be different than 12 hours per week. If you fail to reject the null hypothesis, you do not have enough evidence to say the average is different than 12 hours per week. I want you to start putting your minds in the frame of being a statistician, and what your goal is in this unit is to either reject the business as usual or fail to reject. And when you fail to reject, you do not have enough evidence, okay? Keep that in your minds. This is how we're going to proceed through this unit. What we're going to do now is we are going to practice writing our null and alternative hypotheses based on scenarios that we are given. So I'm going to teach you how to do this, how to set this up. So let's start with number one. A friend of yours claimed that 20% of adults smoke. A recent Gallup survey of 1,016 randomly selected adults showed that 21% of the respondents smoke. So we want to state the null and alternative hypothesis for this exact example. So I want you to think about what's happening just for one moment. Your friend claimed that 20% of adults smoke, meaning business as usual. So I'm going to go ahead and write that the null hypothesis is that the proportion of people who smoke is 20%. But you saw one survey that said 21%. Notice we're not specifying that the researcher believes that the percentage of adults who smoke is greater than 20%. We just found something that showed a difference. So we are going to note that the alternative hypothesis is going to be that the proportion does not equal 20, that there's some sort of difference. So I'm going to make a note here. We don't specify greater or lesser than 20%. So we use not equal to. This implies we have a two-tailed test. This will come into play later on. So it's helpful to note what kind of test we have. Remember, it was just one survey that showed it was 21%. So if we looked at several surveys, we may find that they're either less than 20% or greater than 20%. I feel like nowadays, you know, as time continues on, that percentage is definitely getting smaller, right? Don't you see that? It's almost like smoking was like a, you know, a 90s kind of thing. Like I really don't see it all that often anymore. I don't know, you guys might have different experiences, but it seems like that's, you know, phasing out slowly. Let's take a look at number 2. When parents use XORT method of gender selection, the proportion of baby girls is 0.5. The latest actual results show that among 945 babies born to couples using the XORT method of gender selection, 879 were girls. Okay, let's think about everything that's being presented to us. We are told that using that method, the proportion of baby girls is 0.5. So the business as usual hypothesis is going to be that the proportion is equal to 0.5, 50%. But look at the actual results. Among 945 babies, 879 were girls. What information does that give us? What should we investigate with our calculators?
2879 divided by 945.
Yeah, let's investigate what that means. If there are 879 girls out of 945 babies altogether, go ahead and punch this into your calculators.
It's about 90.93 are girls, so 93% are girls.
Holy crap. This is actual data, right? This is essentially data that has been collected. It's not like a single instance. 879 were girls out of 945. So our alternative hypothesis is definitely that we're going to investigate and see if the true proportion is actually greater than 0.5. We're going to run a hypothesis test to determine if, hey, if these parents use the XORT method, are they always going to get girls, right? Is that going to be more likely for them to have female children? Good. Excellent. I like that we are investigating what's happening based on information we were provided. Let's try number 3. Reports say that the mean birth weight of babies, by the way, when you see mean birth weight of babies, what notation are we referring to? Mean birth weight of babies.
Would it be the mu?
Yes, it would be the mu. Very nice. Mean birth weight of babies. Right away, you're thinking population parameter. Good. So the mean birth weight of babies of European heritage is 3.5 kilograms. Marta wants to perform a significance test to see if this holds true in her nation. She takes a random sample of babies and observes a mean birth weight of mean is equal to 3.43 kilograms. This is actually really, this is really interesting again, because she takes a random sample, finds that it's 3.43. So let me write down the business as usual hypothesis, your null hypothesis, and that is that the mean birth weight is 3.5 kilograms. But she took one sample and she found that the mean was 3.43. How do you think we would write the alternative hypothesis? What's your thought? Would you say it's less than, greater than, or not equal to? What are your thoughts?
Would be
Less than?
It could be, right? It could be, but that was one sample that she took.
So not equal to.
Yes, good. We're wondering if it's actually different, right? We don't have enough evidence to sway us in one direction or the other. So to be safe, we're going to say, is it different? So mu is not equal to 3.5 kilograms. We're trying to investigate if something is going on. And it may help if I write down, is the mean weight of babies different than 3.5 kilograms? We want to know, we want to investigate what's actually happening here. That one sample did show it was less, but how do we know if we don't take another sample, if it's greater or what's going on, right? So we want to be safe and say, is it different? Surujni.
So we only know that because she took a random sample, just a few people, not like everybody.
Right, it wasn't like number 2, where we had 945 babies and we determined their gender and we saw 879 of them were female, right? That's a huge difference. This evidence here is much different from what we saw in this case, which is just a random sample. She took a random sample. So we just know that there might be something going on. So to be safe, we don't claim one direction or the other. We say, let's check to see if there's a difference. Okay. Oh, I do want to include for number 2, with this P is greater than 0.5. This is actually a one-tailed test. Right? It's one direction. We're seeing if P is greater than a particular value. That's a one-tailed test. When we refer to not equal to, we're not sure if it's lesser or greater. This is a two-tailed test. Okay, the only time it's a two-tailed test is if it's not equal to. I want you to check out number 4. Just take a minute. I'll read it to you. I want you to think about what you may write. A city had an unemployment rate of 7%. By the way, if you're not sure whether to use P or mu, remember what mu stands for. Mu is the mean, whatever value it is, right? That's the average, the mean. If you're given a percentage, think proportion of the population. Percentage proportion of the population. Lots of P's there, lots of alliteration. A city had an unemployment rate of 7%. The mayor pledged to lower this figure and supported programs to decrease unemployment. A group of citizens wanted to test if the unemployment rate had actually decreased. So they obtained a random sample of citizens to see what proportion of the sample was unemployed. Go ahead and write down your null and alternative hypotheses. What I'd like from all of you is to see what you think those hypotheses are in the chat. Send your answers to me directly. I'm going to pause the video for 60 seconds. The first thing we'll note is that the business as usual hypothesis, right? The null hypothesis in this case is going to be that the proportion is equal to 0.07, okay? Now, we're not talking about the average. We're talking about the percentage of the population, which is proportion. So that's P. Next, our alternative hypothesis. Think about the language that was used. The mayor pledged to lower this figure, right? And the group of citizens want to see if it actually decreased. So we want to determine, we're specifically stating we have a case here, and we'd like to see if that proportion is actually lower than 0.07. The researcher is interested in determining that. And the researcher in this case is a group of citizens. Does that make more sense to everyone? Awesome. That's okay. That is okay. I'm going to underline here that the mayor pledged to lower this figure. And then the group of citizens wanted to test if the employment rate had actually decreased. So that's their goal. They wanted to test if the rate had actually decreased. So they want to know, is it less than 7%? Is the unemployment rate less than 7%? Think about the fact that, you know, if the mayor is pledging to do something and the mayor is funding specific programs that are aimed at decreasing unemployment, well, all right, let's see if this is true. Let's investigate and see if the mayor is doing exactly what they said they would do. So think about that perspective. They want to determine if it is in fact actually happening. Good. Because we have the proportion being less than 0.07, this is a one-tailed test. Good. Let's try a couple more. Go ahead and turn the page. You have numbers 5 and 6. I will read them both aloud and give you an opportunity to try these. Number 5. A fast food company advertises that the pre-cooked weight for its burgers is on average 0.2 kilograms. The company runs a regular quality control test that involves weighing a sample of burgers to see if the burgers are too light or too heavy. Hint, hint. If the sample mean weight is significantly different than 0.2 kilograms, then they recycle the entire batch. Go ahead and write out the null and alternative hypothesis. 30 seconds starting now. You should have for your null hypothesis, the business as usual hypothesis, that the mean, notice it said average, right? It's on average 0.2 kilograms. So the mean is 0.2 kilograms. We are determining if the sample weight is significantly different than 0.2. So significantly different means that it could be greater or lesser, but the point is it's not equal to 0.2. So you have equal to and then not equal to. So here's our two-tailed test. I also do want to point out there was a hint in this, and that is we're determining essentially if the burgers are too light or too heavy, because that's a problem either way, right? You want to make sure that they're consistent standard, they're consistent weight. If it's too light or too heavy, sorry, they're not going to be accepted. So it's definitely a two-tailed test. Beautiful. Number 6, a restaurant owner installed a new automated drink machine. The machine is designed to dispense 530 milliliters of liquid on the medium-sized setting. The owner suspects that the machine may be dispensing too much in medium drinks. They decide to take a sample of 30 medium drinks to see if the average amount is significantly greater than 530 milliliters. Go ahead and write out both of your hypotheses. Starn, excellent. Okay, so let's take a look. Starn, that one was 5. So for number 6, your null hypothesis, notice that we are looking at the average dispense for the medium-sized drinks. So we're saying that it is going to be equal to 530 milliliters, right? That's the null hypothesis, that's business as usual. But the owner suspects that it might be dispensing too much liquid. So he or she wants to determine if that average is actually greater than 530 milliliters. So nice work, everyone. Right? We are looking to see if the average amount is significantly greater than 530. So that's essentially what we're testing here. And as a reminder, this is a one-tailed test. Beautiful, beautiful work. Now let's talk about the types of errors we can make if we fail to reject or we reject the null hypothesis. Okay, everyone, please carefully watch what I'm about to show you. And start, no worries, that's no worries at all. Okay, we have a table here that I want you to refer back to. This might even be a table that you write down, or maybe you cut out of your notes and you put on your formula sheet. I don't know, but you definitely want to keep this table handy, because I will ask you on your final exam to, and many times in this packet of notes, to determine what kind of error you could have made. So here's how we read this table. If you, so I'm going to say start here, start here. You start in this column. If you fail to reject the null, and the null hypothesis is true, then you made a correct decision. You said there wasn't enough evidence to get rid of the null. There wasn't enough evidence to say that the null wasn't true. And the null hypothesis is true, so we made a correct decision. We could feel good about that. However, if we fail to reject the null, but it was in fact false, we made what's called a type 2 error. Okay, if we fail to reject, but the null hypothesis is false, we made a type 2 error. The probability of that error is referred to as beta. We are not going to calculate beta. This is something for like stats 2. This is something for a future class. So what may help everyone is to keep this in mind. If we fail to reject the null, we could have made a type 2 error. Okay. If we in fact rejected the null, but the null was true, then we made what's called a type 1 error. And the probability of that error is alpha. We will talk about that in this particular packet of notes. Okay, so to help you out again, if you fail to reject the null, you could have made a type 2 error. If you rejected the null, you could have made a type 1 error. So those go hand in hand. All you have to do is remember that they go hand in hand. Okay? If you want on your formula page, you can say, if you fail to reject the null, you could have made a type 2. If you rejected the null, you could have made a type 1 error. Keep that in mind. I write it out here below for you, just so that you have it described in a different language. But I think it may be beneficial to you to literally write out, if you fail to reject the null, you could have made a type 2 error. If you rejected the null, you could have made a type 1 error. Okay, keep that in mind. You're going to need that information for future problems. What I mean by rejecting the null is saying that we have enough evidence to say that there's something significant happening, right? What we're going to be doing in this unit is we're going to be deciding if we can say that the null is not true. Like for instance, let's go up to this one. Let's take a look at number 6. Let's say that the owner is being told that his machines are in fact dispensing 530 milliliters. But he's watching these cups go out and he's thinking, no, it's not. It's dispensing more. So he runs this hypothesis test. He is determining whether or not the average is actually greater than 530. A statistician does their thing, and then they show that, guess what? We can actually reject the null. There's enough evidence that shows that this is not the case. That automation, that automated drink machine is not dispensing exactly 530 milliliters. So that's what we mean by rejecting the null. We are saying, no, this is not actually true. There is something significant going on. Right? So we're going to reject the null. That's what I mean by reject. Does that help, Emma? Let me give you a real world example. Aha, Anthony, thank you so much. Very cool. I'll share that with everyone. Think about this real world example. So we're going to compare the possible outcomes with a person on trial in our court system. Think about this person on trial. That person is either innocent or not. Now remember, they're innocent and proven guilty, right? So the null hypothesis would definitely be that the person is innocent. The alternative is that they're not. But don't you have to have enough evidence to show whether or not they're guilty? You have to be able to prove that they're guilty. They are innocent until proven guilty, which is actually really perfect for this kind of understanding of hypothesis testing. So there are two correct decisions that could be made. The first is that the person is innocent, okay, and we failed to reject the null hypothesis. In other words, we agreed with the null hypothesis that the person was innocent. The other correct decision is that the person was not innocent and we rejected the null hypothesis. We said, wait a second, it's not true that that person was innocent. We have enough evidence to show that they were guilty. So these are the two correct decisions, right? They were innocent. We proved that they're innocent. The evidence shows they're innocent. So we do not reject the null. The other version is that they're not innocent, that they're guilty, right? And we have enough evidence to show that they're guilty. So we reject the null. We're like, no, this person is not innocent. Emma, awesome. I'm really, really glad. But check this out. And this unfortunately happens in the system all the time. It's terrible, but it happens all the time. There are two incorrect decisions that could be made. So we could have made a type 1 error where we rejected the null hypothesis that the person was innocent. We rejected it, which means we're saying, no, they're not innocent, they're guilty. If we rejected the null hypothesis, but it was actually true, we just sent an innocent person to jail. That's a type 1 error. If we made a type 2 error, where we failed to reject the null, but the null hypothesis was false, meaning they were actually guilty, we just let a guilty person go. I hope that you're visualizing what's happening here, right? Think back to the table before. Sujani, thank you. Think back to that table before where if you failed to reject the null, you could have made a type 2 error. And if you rejected the null, you could have made a type 1 error. So I want you to make that connection, right? Here, we reject the null. We're saying, no, the person is not innocent, but they actually were, right? And then with type 2, we failed to reject the null. We didn't have enough evidence, but they were in fact guilty. And so we released them. Good. Always feel like you can come back to this section just to kind of read it through it again and make that connection with the real world so that it's easier to understand the decisions that we're making and the types of errors that could come from those decisions. So here's the summary. For any hypothesis test, you can have 4 outcomes. You can either have 2 correct decisions or 2 incorrect decisions based on the null hypothesis. Remember that when the decision is made about the null hypothesis, nothing has been proven. It's business as usual, right? We cannot say that anything specific is happening. There's no difference in what's business as usual. So nothing's been proven. We're just saying we don't have enough evidence to show otherwise. Both decisions can lead to errors, just like we saw above. So just like in our court system, we haven't proven anything. We can only make a decision based on the evidence shown. Do we have enough evidence to show there's a difference? Okay, reject the null. Do we not have enough evidence to show there's a difference? Okay, we failed to reject the null. There's just simply not enough evidence. Excellent. Okay, let's get into looking at p-values now, in which case you are going to need your z-score tables. So make sure you have those handy. I'm going to read through this and then we're going to use those charts again. There are types of hypothesis tests that we can use. In this class, we're going to be using the p-value method. So that probability, right? We're looking at the probability in those tails, just like we saw in previous units. The p-value method involves determining likely or unlikely by determining the probability. So assuming the null hypothesis were true of observing a more extreme test statistic in the direction of the alternative hypothesis than the one observed. If the p-value is small, say less than or equal to alpha, then it is unlikely. And if the p-value is large, say more than alpha, then it is likely. So I'm going to write a statement here that I think will be really, really helpful to all of you. So I want to make a note that if your p-value is less than or equal to alpha, we will reject the null hypothesis. There's a statement that I like that makes this really easy. Like when I was thinking about learning this again, this statement that I read somewhere says, if the p is low, then null must go. If the p is low, then null must go, right? Notice your p-value is smaller than alpha, so you reject it. I am going to write that down, even though that's kind of a goofy statement. If the p is low, meaning lower than alpha, the null, meaning the null hypothesis, must go. You like that little rhyming action, huh? Yeah, you do. Yeah, you do. Everybody likes rhymes. If the p is low, the null must go. Keep that in your mind. So in which case, if the p-value, notice the less than or equal to alpha. If your p-value is greater than alpha, it has to be greater, then you fail to reject. I apologize for squeezing this in here. Okay. So if the p-value is greater than our alpha, you fail to reject the null hypothesis. There's something called the rare event rule for inferential statistics, and that is if under a given assumption, the probability of a particular observed event is extremely small, we conclude that the assumption is probably not correct. So rare events are important to consider in hypothesis testing because they can inform your willingness not to reject or to reject a null hypothesis. So we may see that in this set of notes. Let's turn the page. And please grab your Z tables. Ta-da. We are going to find the p-value for two-tailed or one-tailed tests. We have a two-tailed test when the test statistic is z is equal to 1.34. When you think of two-tailed, I want you to think of both tails being shaded in. So we're going to plot the point 1.34. That's approximately here. We're going to draw our dotted line up. So this is where z is equal to 1.34. But remember, it's a two-tailed test, which means z is also going to be equal to negative 1.34. I'm going to make a note of that. Z is equal to negative 1.34. Isn't it nice that I copied these curves here so you don't have to draw it by hand? That also means I don't have to draw it by hand, and it is a relief. So go ahead and use your z-score table. We all know how to use this bad boy, and I would like you to tell me what is the area to the left of a z-score of negative 1.34. Share when you have it. negative 1.34. Double check that. Emma, double check that. Negative 1.34. Jenny, excellent. So according to my chart, when I look at negative 1.34, let me scoot this down. Oh, I can do it. I can do it. I can scoot it down. There it is, the 4 column. We see that the p-value is 0.09012. Emma, no worries. 0.09012, which implies that the area above is going to be the same because our curve is symmetric about the mean. So both areas are the same, which means we have a combined p-value. So our p-value is going to be the sum of both of those tails. Which is equal to 0.18024. 0.18024. Now remember, we're not making any decisions right now. We have no information about alpha. So Suhujini, no worries. We have no information about alpha, so we're just looking at p-values. That's all. We want to take baby steps here to make sure that we understand every tiny little aspect of the process. Okay, number 2, we want to look at a left-tailed test. When the test statistic is z is equal to negative 1.84. This is not a 2-tailed test, so we're not shading in both tails. We're just shading in the lower tail, right? The left side. So z is equal to negative 1.84. That's approximately here. And since it's a left-tailed test, we want to shade the region to the left. Go ahead and look in your z-score table, and I would love for you to share the area to the left of a z-score of negative 1.84. Leah, perfection. Emma, perfection. So we see that it is 0.0, Nick, excellent, 0.03288. 0.03288. So we will write that our p-value is equal to that. 0.03288. Isn't it so wonderful that we're still using the same stuff that we've been looking at this entire time? It doesn't go away. That's the beauty of math. Let's go ahead and turn the page. Let's look at another one.
I have a quick question before we turn. It's on the same page.
Yeah.
The first one, when were the 0.9012, since we, oh, never mind. I was thinking if 1 would be like different, like if we would have to look on the other side of the table to get the positive 1.34.
No, only because it's symmetric. So if you know this tail, you'll know that.
Yeah, I just realized when I look back.
Ah, okay, beautiful, beautiful. Take a look at number 3, right-tailed test. When the test statistic is z is equal to 2.95. Let's go ahead and plot that. Z is equal to 2.95. I'm going to try to shade this in, even though it's like really hard to see. That's shaded in. That's totally shaded in. How do we figure out that region? What do we have to do to figure that out? Oh man, Nick, you are so good. How did you figure that out?
I did 1 minus 0.9984. I literally went on the positive side because I knew that was like shaded to the left, and I figured out like it's a whole, so 1, so and then subtract it.
Yes, perfect. So you're basically saying, I didn't forget all the training that I've had so far. You're like, I know how to find the region to the right because the table gives me to the left. So I subtracted from 1, which is total probability, to find the region to the right. I didn't mean to write 159. Hold on. It should be 16. That's my bad. I had a different table last time. So 0.0016 is correct. Perfect. Nick, that's beautiful. So the p-value is equal to 0.0016. Very nice. Excellent. Cool. All right, let's summarize this. Find the test statistic and its associated p-value. Critical values and confidence intervals will not be covered in this class. Take a look at the visuals. You have your two-tailed test. That's if your alternate hypothesis is not equal to. You have a left-tailed test if your alternate hypothesis shows less than, left. And you have a right-tailed test if your alternate hypothesis is greater than. Okay, I'm going to rewrite these in a different way because the notation is a little bit different. Sometimes you'll see H sub 1, sometimes you see H sub A. I prefer H sub A for alternate. So if it's not equal to, it's a two-tailed. If it's less than, it's a left-tailed. And if it's greater than, it's a right-tailed. Okay, keep that in mind. Good, this is like your key. All right, we've already discussed the fact that if the P is low, the null must go. So here we have it reiterated. If the p-value is less than or equal to alpha, reject the null hypothesis. If the p-value is greater than alpha, then you fail to reject the null hypothesis. You essentially don't have enough evidence. So what we would write in our conclusion, think about the fact that when we were talking about confidence interval statements, do you remember how we kept referring, like whenever we wrote our conclusions, we kept referring to the same phrase? We literally wrote it the same way again and again and again. And we'd be like, we are 95% confidence that our true, the true value of our proportion, blah, blah, blah. We've said the same thing. It was kind of cookie cutter, repeatedly, same idea. So for this particular section, when we write our conclusions, we're going to use the same framework, which is nice because essentially all of our answers will look identical because we're using the same language. So I'm definitely going to put a bunch of stars here to kind of really get us comfortable with how we will write our statements, just like when we were looking at confidence intervals and writing those conclusions, okay? So if you reject the null, if that is your decision, what you're gonna say is the following. There is sufficient evidence at the whatever level of significance it is, we'll discuss that in a moment, to show that, and then you state the alternative hypothesis. So there is sufficient evidence at the blank level to show that the alternative hypothesis, blah, 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 okay? I'll show you what I mean by this. And then if you fail to reject the null, if that's your decision, then you will say there is not sufficient evidence at the level of significance to show that the alternative hypothesis, okay? Let me show you what I mean. On the page when you're ready. And let's do this. We're going to put all this stuff together. Okay. For the following examples, assume that the level of significance is alpha is equal to 0.05. That's very important. We're actually given alpha this time. So definitely something we need to use. Because remember, we want to compare the p-value and the alpha. That's going to help us a lot. So the percentage of blue M&Ms is greater than 5%. The hypothesis test results in a p-value of 0.0010. So we're going to start by specifying the null and alternative hypothesis. Okay, remember the null is business as usual. So the null hypothesis in this case is that the proportion, the percentage of blue M&Ms is equal to 0.05. But what we are testing is if that proportion is actually greater than 5%. So if it's greater than 0.05. I'll give you a second to write that down and to think about that fact. Business as usual would be that it is 5%. We are looking at determining if it's actually greater than 5%. What kind of a tail is this? What tail test is this? And go ahead, I'm just going to let you answer that. What do you think?
It is a right-tailed test.
Yeah, excellent, excellent. I'm going to write that down. This is a right-tailed test. Thank you for giving me the direction. I didn't want to like hint at anything, so that's why I refrained. So I really appreciate the fact that you gave me a direction on this. As a reminder, what will be helpful to you is maybe to write this down on this page, and that is if the p-value is less than or equal to alpha, remember your decision is to reject the null. But if the p-value is greater than alpha, you're going to fail to reject the null. Those are the two decisions we could make. So this is something I want you to maybe write down a couple times, just so that you're really feeling comfortable with that. So that means we have to compare the p-value with alpha. So our p-value, we're told, is 0.0010. So 0.0010, here's our p-value. We also have to compare it to alpha. Alpha in this case is 0.05. Well, do you see that alpha is actually greater than the p-value? So you're opening up to alpha. Does that make sense to everyone? Since the p-value is less than alpha, our decision is going to be to reject the null. So we are going to reject the null hypothesis since our p-value is smaller than alpha. And now let me show you how you write your statement. There is sufficient evidence at the, now we need to write out the level of significance, and the level of significance is our alpha, which is 0.05. So there is sufficient evidence at the 0.05 level of significance to show that, and then notice what the alternative hypothesis is, and that is the percentage of blue M&Ms is greater than 5%. So we're going to write that to show that the percentage of blue M&Ms, whoa, I can't write the word blue. Wow, I'm struggling. Let's try that again. Of blue M&Ms is greater than 5%. Cool, done. We use the exact framework that we mentioned from the previous page, how we would write our conclusion based on the decision. So we reject the null, we say there is sufficient evidence at the 0.05 level of significance to show that the alternative hypothesis is true, that the percentage of blue M&Ms is greater than 5%. Cool. Stephanie, go for it.
So would this be on the take-home part of the final or on the multiple choice?
Yeah, more so the take home. This is actually not fully everything you would do for one of these questions. This is like half of what you would do. So yes, this and a little bit more.
Okay, thank you.
You're very welcome. Good. Any other questions? I think we have time for one more. Let's just do one more. Fewer than 20% of M&M candies are green. The hypothesis test results in a p-value of 0.0721. Specify the null and alternative hypothesis. Would someone tell me what is the null hypothesis in this case? Give it your best shot. What would I write for the null? Don't be shy. Sam, what'd you write for the null?
Would it be that P is less than 20%?
That would be what you're testing. Think about the boring one, right? The one that's super boring. And the fact that it's just equal to it, right?
So
Your null hypothesis, go for it.
Is it a
I think
20%?
that it was equal to.
Yes, the null hypothesis is actually always going to be just the equal to. Good, good. Now the alternative hypothesis, that's what we want to test. And then what you said, Sam, in that statement, that's where I'm going to write P is less than 0.20. Good, very cool. Remember the null hypothesis will always be that equals. It's a boring one. No difference. It's just is what it is. And remember, is in math means equals. Good. So we've got both of our statements. What kind of a test is this?
It's a left tail test.
Yes, it is. We're going to write left-tailed test. Perfect. I'm going to note here that we have a p-value of 0.0721. By the way, you're probably thinking, what's the alpha? If you go to the very top, it says, for the following examples, both of them, assume that the level of significance is alpha is equal to 0.05. So I'm just going to write down here again that we know that alpha is equal to 0.05. So we are going to compare the p-value 0.0721 with our alpha, which is 0.05. I always like writing it directly above just so that we notice that we're looking at the p-value and comparing it to the alpha. Jenny, that's funny what you wrote in there. So notice that the p-value is actually greater than our alpha. So we're going to write that it's greater. And then according to our little cheat sheet above, if the p-value is greater than alpha, we fail to reject the null. So here's the statement. Let's write fail to reject the null. And now we're ready for our cookie cutter statement, which is great because we don't have to get super creative with it. We just literally write the same thing again and again and again. Conclusion. Remember, the decision is to reject or to fail to reject. The conclusion is the write-up. So there is not sufficient evidence at the 0.05 level of significance to show that, and then the alternative hypothesis, we just state that which is fewer than 20% of M&M candies are greens. That's the alternative hypothesis. To show that fewer than 20% of M&Ms are green. Wow, my ampersand sucks. It's terrible. Wow, I can't draw that at all. Jesus. Cool. That's it.
I got a question.
Yeah, go for it.
Where do you get the 0.5 from for the second
Oh,
one?
good question. That is actually at the top. So notice here it says for the following examples, assume that the significance is 0.05. So I use the alpha 0.05 for both of these.
Right.
Beautiful.
Thank you.
You're welcome. For part C, and you can take this home with you. I'd actually love for you to just finish this. For part C, the alpha is still 0.05. So just go ahead and take this home with you. That way on Monday, I can bypass this problem. So I would like for you to just take this home, do this, and we can quickly run through what I wrote, but I'm actually going to fill this in on my own as well. Okay, take this problem home with you. And on Monday, we will continue by testing a claim about a proportion. Excellent work, everyone. Fantastic job. I will take any questions about your unit 7 at this point, but otherwise you are free to leave. I will see you all Monday. Have a fantastic weekend. Make sure
Thank
you're
you,
doing that
Professor.
work.
I have a question.
Yeah.
So for mine, it's on the multiple choice. It's not on the other one where the with the mini tab. It's the other one. It's question 7 with the graph. I keep getting 2.8 out of 3 on that. I have the 2 bottom ones correct. And I think I don't know if it's like something wrong with the graph or something, that I keep having issues with that.
Is it the one where you plot the points?
Yeah, I think I emailed you about it before break, and I see that you dismissed one of the
I
question
did.
before that.
Yeah, I
Question
did
5.
because it was kind of absurd. That whole dot plot thing is kind of a bummer because, so let me show you. I'm going to show everybody this. Actually plotting, sorry, I filled these in myself. Where is it? Like actually plotting this out, it can be a little bit tricky because you don't actually have the values there. You just kind of like have to estimate
Eyeball it, yeah.
possible. So what I can do for you is I can easily just give that right back.
Okay.
I'll give that
I
right.
was worried about that. And then the other one is the one right below that. You just have to and I mean see what I said for that, right?
The one, yes, that is absolutely correct. So the one that I had to clear all my answers. The one that is where you are explaining a particular ordered pair, which is this one. So
Mhm.
you'll write out your meaning of the ordered pair, and then I will physically go in this after the due date, and then I'll award credit if you earned it for this particular problem. So yes.
Okay.
That
All
manual.
right. Otherwise, I'm all set with both of them. I turned in the mini tab assignment already, so I'm all set.
Yay. Okay.
I
Very
have
cool. Excellent work.
Question as well.
Yeah, go for it.
For question 2, how do I do that one?
Let's see, question 2. So what you'll want to do is you'll want to use Minitab. Are you using Minitab at all?
I didn't use it for this one.
You want to. So what you'll do is you'll just copy the entire list just like this, copy, paste it into Minitab, and then you'll run a regression analysis. If you are unsure as to how to run that regression analysis, let me show you where you would find the instructions. Now, keep in mind, you want that equation, right? So let me show you that the actual assignment, the Minitab assignment, actually tells you how to do that. So you'll start by creating you can start by creating a scatter plot, and then you can determine the linear correlation coefficient, and you can also create the line of best fit. This is the regression line, and it'll give you the equation that you need. So you will have these instructions, which will help you to do that. Once you have your data in there, you're just going to click stat, then regression, then fitted line plot. You'll double click that the response is your Y. You'll double click that your predictor, right? The predictor variable is X. You'll select linear, that might already be selected. And then you can click OK, and it'll give you the equation that you want. And that will help you to answer this question where it says, hey, what's the equation for number 2? Okay, so you'll use Minitab to do that. You can also do this in Excel.
And I also
Just like that. I'm sorry. I'm sorry. I was gonna say just like that. You can do Excel, like
Oh,
just
yes,
there are 2
yes.
columns.
The Excel instructions are different, so you
That's
want to watch
okay.
my Excel video.
Okay, yeah.
Perfect. Stephanie,
Professor.
oh yeah.
So actually, I don't have a Minitab, so I try to use an Excel for question number 2.
Cool.
And the problem here is that, as because I speak different languages, like all the settings are in Excel or in different languages. So I had a hard time to do whatever you instructed us on the video. So
Okay.
I was wondering if there's any other way we can figure this out other than using Minitab and Excel.
There might actually be a way to do this here. So regression line for, for a set of data, I would just type it in. Let me see. Quick linear regression calculator. This might work. So if we're in Lumen, let's take the X values, and I'm just going to highlight. Let me do something here. Oops. Because we want just the X values and just the Y values. So I don't want to copy all of them. That's not what we want. Give me a second. What I'll do is I'm going to use Excel. I'm going to copy the values here. And then I'm just going to select the values in this column. Let's see if that works. Yes, it did. Let me go back to Excel. I'm just going to use these values, copy that, paste them here. And now let's, let me see the calculator. Yes, if you just, okay, good. So calculate the regression equation, and there it is.
Oh,
So there you go. This works. I'm going to send this to you.
all
Not
right. Thank you
that,
very much. Yeah.
Let me stop sharing, and I'm going to put this in the chat in case for whatever reason Excel is not working for you. You can use the online.
That
set.
one was easy. I feel like that was easier than
Yeah, it is. But for the project, you need like the scatter plot and all that stuff. So while the equation is easier, I still would, make sure you're comfortable using Excel or Minitab.
okay.
Awesome. Holly, you
And
had your
it's
hand raised.
oh.
I'm so sorry.
Yeah, that Excel video you're talking about, where is that in Lumen? I'm trying to look for it, but
It's in your Zoom lecture recordings where all of our
okay.
where all of our videos are. So if you go into Zoom lecture recordings,
Mhm.
it's right here. Creating a scatter plot with line of best fit in Excel.
Ah, okay. Okay, thank you.
You're welcome.
And this is still tonight, right? The due date is today still.
For
Today.
your homework, let me extend that.
Oh, thank you.
I have a question on number
Subtle
9.
way of saying, can you extend that? Done. Okay, it's extended.
And it's the same time, the 5th, it is the other one too, right? It's the homework. The application is still
Yeah,
the 5th.
yeah.
Okay, thank
I
you so
do
much.
have
Oh
to
my
give
God.
you guys due dates on 8 and 9. So we'll do that. But we'll talk about that next time on Monday. Next question.
Question number 9.
Number 9 from our homework, correlation and regression. Let's look at number 9. 7.
Thank you.
You're welcome. See ya. Okay, cool. For number 9, they are given 2 points that they would like you to use to write the equation of the line. So this is going back to your last class. If you do not remember how to write the equation of the line, do not fear. I sent you an email, I think over the weekend, I think around there, which included a link to my video, which describes how to write the equation of a line when you're given 2 points. So I would like for you to use that video to help guide you in writing the actual equation. Remember the process. If you have 2 points, you need to find the slope. Then you use point slope form to then derive slope intercept form. The other thing you want to consider is that P is your price in dollars. So P is your X. And Q is your quantity of cable, so Q is your Y. Okay, just keep that in mind. You have to
Would it be like that other question where it was like Q equals and then the X plus that?
Yeah, it's like MX plus B, except it's going to be MP plus B. So it's Y equals MX plus B, which is slope intercept form. You're going to use that equation of the line. Just remember to replace Y with Q and P with X, those variables. They want you to use the specific variables.
Sounds good. Thank you.
You're welcome. Awesome.
Can you explain number one? Like I've been trying to figure out the scat like I
Yes.
tried it and
What's going to be helpful to you is thinking about what these coefficients actually mean. So if you had a Pearson correlation coefficient of a negative 0.98, that's a very, very strong negative correlation, right? So that those dots follow a very tight line. So what I would think about in this case is the fact that your dots will follow some sort of line that's negative, so something like this, and they're very tight to that line. So your dots are going to be like, you know, they're really close. Oh, I can't do this. They're like really close. Even though they're still scattered, they're pretty tight to that line. Okay. Oh my God, I'm having such a hard time with this. But you see what I'm saying? They're really close to that line. For a Pearson correlation coefficient of 0.09,
it'd be closer to 1, so it would be very strong.
No, this is really close to 0. Think of this as like 98 cents, right? So you're close to $1. This is only 9 cents.
Oh yeah.
This is like ridiculous. So it's a positive correlation, but there's almost no correlation. It's so small. So something like this would be like, there's no direction. All the data values are all over the place, and there's no like rhyme or reason going on there. Same with this one. This is a negative correlation, but same exact idea. It's almost like chaos, right? But it's going in the negative direction. So it's still kind of sloping downwards, but the points are all over the place. So it doesn't really seem like there's any correlation. And then with this last one, a positive 0.91, this is that opposite scenario where you see that it's a very strong positive correlation, such that when you look at those dots, they're really close to that imaginary line of best fit. You have to visualize that line, right? They're going to be very close to this tight line. Okay. Okay, you got this. You can do this. And I'm drawing lines all over the place. Let's see. That is embarrassing. All right, everyone. I'm going to give you an opportunity to play around with this. Please don't hesitate to reach out, but I will see you all on Monday. Excellent work today.
I have a quick question.
Yeah, sure.
I was wondering if I could meet with you either tomorrow or Friday or whenever you're available to go over some chapter 6 homework questions.
Yeah, sure. Let's do the whole email thing. We'll figure out when we have a time that works out.
Okay, so do you want me to email you now and
Yeah, sure. That'd be great.
just ask you when you're free or something?
Let me know when you're free.
Well, I only have 2 classes tomorrow at 11 to 1